in Durban, so we don't have a mountain in Durban, but we do have the best stadium, I think, from 2010. And also a beautiful beach front, which they fixed up for the World Cup. So that's a picture of Durban. And I'll be talking about photosynthesis. So there have been quantum effects detected in the photosynthetic process, so I'll just be discussing how we can use quantum mechanics to better understand photosynthesis. So since the beginnings of quantum mechanics in the early 1900s, people have speculated, these two famous people in particular, that perhaps quantum mechanics will play a role in helping us to understand on a small scale or more in detail how life works. Okay, so in fact, we don't yet have a complete theory of biology in terms of being able to derive biology from quantum mechanics and then quantum chemistry and then biology. So this is one of the open questions. So of course, the ultimate or the most beautiful goal or achievement of quantum biology would be to understand or help to contribute to answering the question of what is life. So how did life spontaneously emerge from inanimate matter and questions like that. But unfortunately, we haven't reached that state of the art yet. So the next question we could ask is, are there aspects of the functioning of living systems that necessitate a quantum mechanical description? So we know most biological processes are fairly well described classically, but are there some aspects of living systems that require a quantum mechanical description? Okay, even if we failed answering that question, we can apply the knowledge that we've learned along the way to engineering. So yeah, these are the questions that quantum biology addresses. So actually, since most of you are not in the field of quantum biology, let me just define what it is, because we all know that quantum mechanics describes the equilibrium properties of molecules. Okay, molecules are obviously ultimately and fundamentally described by quantum chemistry. But can this fundamental description of a complex system like a biological system actually add anything to biology? So what is quantum biology? It's not about the role of quantum mechanics in equilibrium systems, but it's rather about whether living processes that contribute to the living of living systems necessitate a quantum mechanical description. So do quantum effects play a role in understanding biological processes? So quantum biology in its current state involves the following areas. So the most well-established area is the study of photosynthesis. So you've already heard about the proposal that quantum effects play a role in magnetoreception in birds and also in some other animals, like turtles and so on. And then also in enzyme catalysis and so on, but I'll be focusing on photosynthesis today. So some people say that quantum biology is a new field. I would say it's just become more, there's been a revival of interest in the field recently, because in fact the field, in my opinion, started in 1938. That was the oldest proposal that I could find, that quantum mechanics may play a role in certain biological processes. And we've heard from a chart that the proximity of the pigments in the photosynthetic light harvesting complexes kind of, I don't think it's that surprising that there's some kind of quantum coherence involved in the transfer process. Anyway, yes, it is not so surprising. It was already thought of in 1938. David Schrödinger famously asked what is life in his sort of popular science book of 1944, an interesting read. And then I think the first experimental evidence of quantum effects in photosynthesis was already back in 1966, when it was shown that electron transfer rates in fact increase with a decrease in temperature. So classical or standard theories of electron transfer are that it's a thermally activated process. So obviously if it speeds up when you decrease the temperature, this is a non-thermally activated process, and quantum mechanical tunneling was claimed to play a role, or proposed to play a role. Okay, they did some other experiments, but the ones I'll focus on today were in 2007 and 2010. Two groups from Toronto and from Chicago, from Berkeley as well, started to do experiments on light harvesting complexes in green sulfur bacteria and some types of marine algae. So now these are both photosynthetic organisms that operate well under low light conditions. So, for example, the green sulfur bacteria that I'll talk about was found at a depth of 2,500 meters under the sea. So as you can imagine, it's pretty dark down there, and every photon that comes, you need to use it. So this is why these organisms are probably it's even more essential for them to be efficient than it is for the kind of higher plants that operate on the surface of the Earth. As Chart was talking about, for these kinds of organisms, protective mechanisms are also very important when the intensity of light is too much. So these are particular examples of photosynthetic organisms that are particularly efficient. So we would like to know whether the quantum coherence that was detected in these experiments can contribute to this efficiency. And now you can understand that this efficiency is clearly part of the functioning of this living system. Without this efficiency, the thing would die under the ocean. So in general, or the overall process of photosynthesis, as Charles has said, is actually not that efficient. So there's a typical efficiency of plants. So sugarcane is fairly efficient, just under 10%. So what's the general photosynthetic process? Obviously carbon dioxide plus hydrogen, usually in some electron donor, getting transferred into carbohydrates and the oxidized donor. So the donor can either be oxygen or sulfur, in the case of the sulfur bacteria. So the point is that when I say the process is highly efficient, I'm only talking about the primary stages. So this is when the very first photon hits the antenna system and gets transferred to the reaction center, the subsequent process of electron transfer. These are both very efficient processes. Thereafter, the efficiency decreases, as you've heard from Charles already. So when I say efficient, I'm purely talking about these first two states, the energy and the electron transfer. So what happens? This picture is more like the hopping model that we've heard about from Charles. The Foster hopping model, okay, but it's just a picture to show that basically the pigment separation distances, so the pigments are either the chlorophylls or the bacterial chlorophylls, depending on which bacteria or high plant you're looking at. So they're separated by about 10 angstroms. The transfer time takes like under 100 picoseconds, and the efficiency is almost 100%. So that purple part of the reaction, where the reaction center is based, and after this energy transfer takes place, electron transfer takes place. So what was detected, what you see here is a picture by the Greg Engels group. So this is the quantum coherence that they detected. That thing you see there, the grey stuff is the protein scaffold in which the bacteria chlorophyll molecules are situated. And yeah, this was the experimental result that kind of stimulated the renewed interest in this field. So at first in 2007 they only detected this quantum coherence at 77 Kelvin, but then I think importantly in 2010 they extended the experiments to at room temperature. So this was now clearly showing that in vivo, possibly also these organisms do show quantum effects in terms of quantum coherence during the energy transfer process. So how do we model the system? So we've heard from Charles about this excitation energy transfer. So the approximation that there's a single excitation in the system is in this case a good approximation because the transfer times and the trapping times and so on are calculated, and it's clear that there's one excitation in the system at a time, so we can then use the single excitation description. And then the coupling between the pigments is given by the J's there, so the EJs are just the energy levels of each of these two-level sites. Sorry, a higher excited, so there's the ground state and the first excited state. So we approximate it as a two-level system because any higher excited states decay very fast down to the first excited state. So on these time scales, effectively, you do only have two levels, so the two-level approximation is good here. And the coupling occurs as a result of electrostatic interaction between the chlorophyll or bacteria chlorophyll molecules. Okay, so we've heard from Charles as well that there are these two regimes in which excitation energy transfer can take place. We've heard about the excitons and so on. So in fact, the timescales of the system and the environment in photosynthesis lies in the intermediate regime. So in between the limit where you can consider the system as strongly interacting and the environment as strongly interacting. So it's in this intermediate phase, as we've heard. So making a Markovian approximation where you assume that the environment remains uncorrelated with the system is not actually a good approximation in this case. So now we know that the spin boson model is only solvable in certain cases with this approximation. So this immediately leads to theoretical problems where you are left with models that are either not exactly solvable or not representative of the system. So what we propose is to begin with a simpler model of the environment. So we consider the environment not as an infinite level bosonic bath, but as a spin bath. So this approximation could be good in the case where perhaps only two of the energy levels of each of the molecules of the protein environment are accessible. So perhaps there's only the ground and the first excited state that play a role. Perhaps there are nuclear spins in the environment. Okay, but more importantly for our purposes, we would like to solve something analytically just to show the principle, so a mechanism. So, yeah, I should have said this before. What is surprising about this quantum coherence in the system is interesting for two reasons. So first of all is the question of whether life uses quantum mechanics for its fitness or for its survival. The second question is how quantum coherence can be preserved in such a warm, noisy, chaotic system. So the quantum computer, obviously, you need to preserve the quantum coherence in order to do the computations. So if we can learn lessons of how nature manages to protect quantum coherence on timescales that are surprising through even, or in spite of interaction with the environment, or as we will show, actually enhanced by interaction with the environment. And that's what we're trying to show. So how can interaction with the environment either maintain or enhance this transfer, which is quantum coherent? Okay, so this is just how we model it. So each energy level is coupled to n two-level systems, or n spins. So the bath there is just given by this parameter alpha, which parameterizes the splitting between the ground states and the first excited state. The sigma z's are the Pauli spin matrices, sigma z spin matrices. So the interaction we just take as a simple interaction. We do it as a purely decoherent interaction, so no energy is lost to the environment by the system, because we know the process is 99% efficient, so this is a fairly good approximation. No excitations are lost to the bath. And in this way, our bath Hamiltonian, our interaction Hamiltonians commute, so this is convenient because the states of the system and the states of the bath remain in the product state. We can solve it exactly and find some mechanism via which we can show that the environment, in fact, assists transfer. So what's the simplest transfer system? The diameter, which is pictured there, if you can see it. So we couple each of the levels to the spin bath, which I've said. And then this is a well-known result, that's the maximum probability of transfer is given in terms of J, the coupling between the two levels of the diameter, and the splitting between the energy levels. So you can see by this delta, given by the difference in the energy levels divided by 2, when that's 0, you get a maximum transfer probability of 1. Okay, the dynamics are unitary, so you get this at repeated times, periodic times, you get transfer probability of 1. This is already known. So what we were trying to show, or the main mechanism behind the work, was just to show that interaction with the spin bath can bring these two energy levels into resonance. So the effect of this interaction with the bath, as I've described in the Hamiltonian, is simply to shift the energy levels. This is all it does. We're not losing any energy from the system. So our new energy level is just given there by epsilon prime, and it's given by the old energy level. And then in terms of gamma, which is the coupling with the bath, and n, the number of spins in the bath. So because we have these two parameters, gamma and n, there's obviously a wide range of scenarios where we can get perfect transfer when these two energy levels are equal. And delta is just redefined in terms of those two new energy levels. So through resonance, basically, we can achieve perfect transfer at periodic times in the system. So obviously the interesting question is what happens at physiological temperatures. So we just take the canonical ensemble there to describe the bath at 300 Kelvin. And we show that there are a wide range of parameters, so the effect is robust, for which we can achieve transfers just in the diameter, so we're just moving from state 1 to state 2. We initialize the excitation in state 1, okay, and evolve it using the Schrodinger equation through time, and then we solve it numerically here, tracing over the parameters of the bath, the degrees of freedom of the bath, and then we calculate the probability of arriving at the second state. So that's what's plotted there, and as you can see, for some, and these parameters are kind of biologically irrelevant, so we can achieve good transfers of up to 87% there, even at 300 Kelvin, which, by the way, would not have been possible without the bath at 300 Kelvin. So then, to make it more realistic, we now extend the case of the dimer to a network, so that FMO molecule that I showed you in the beginning where they did the experiment just consists of 7 sites. So anyway, we first just begin with an n-site network. That's the Hamiltonian for the network, so we have equal energy levels in this case, and it's fully symmetric, fully connected network, so we just have equal couplings J between all sites. And again, we have a single excitation subspace here. And then we just calculate the probability, given some we initialize the excitation on the site I of the network. It's symmetric, so all sites are equivalent. And then choose some site F, which we will we'll run the dynamics, and then just calculate the probability with which it arrives at the final site. So this result is known. The probability is 4 over n squared. That's the number of network sites. So the point here is, can we improve this by adding bath or many baths? So we take the network, we take the bath, we take the interaction. We have the same form. Well, this is the Hamiltonian for the network. The Hamiltonian for the bath is the same as before, and the interaction is this purely decoherent interaction as we had before. So again, we have this useful property that the system and the bath remain in the product state. So at 0 temperature, we can solve it exactly. And again, we have this effect where each energy level is shifted, depending on the coupling with its respective bath, if we've coupled the bath to it, and the number of spins nj that are in the bath. So here is just a summary of our results, but the point was that in all cases considered, we could get an improvement from the purely the isolated system network. So adding spin bars, whether you add 1 or 2 or n minus k, is always better than just having the fully connected symmetric network in the absence of any environment. So this is a clear example that there exists parameter ranges where an environment will in fact assist coherent transfer through a quantum network rather than hinder it, which may have been the intuition before. So one of the things through all the mathematics, we find that, again, this resonance principle applies. So if we put one spin bath on the initial site and one on the final site, in the parameter range where they become equal or nearly equal, and it is robust, so they're exactly equal, we find good transfers of up to 86%. So that's in the case where the site 1 and site 2 are the initial and final sites, and these are now different from all other energy levels because of their interaction with the bar. And these are numerical results for 300 Kelvin, again, with the canonical distribution described in the bar. Okay, in the case where we have just a 4-site network and we have the initial and final sites with no bars and the intermediate sites with bars, then again the resonance principle applies. So where the initial and final sites have the energy epsilon and the 2 intermediate sites have some other energy E1 and E2, again we can get good transfers whenever the bath is connected. So you need a bath here. Whenever gamma is 0, you can see the transfer probabilities get bad again, so the bath helps. Yeah. So then we go back to this. This is the antenna on which the experiments were done. It's a 7-site network, fully connected network, where the couplings and the energy levels have been calculated and fitted to the experiment. So we now apply our model to this situation. And so either site 1 or site 6 can act as the initial site in this biological system. So we calculate both, and we find that we can again achieve transfer efficiencies of up to 80–90% for realistic parameter ranges, just by coupling a number of spins. Actually, what we did here is take 10 spins and couple them in all possible configurations to all 7 sites. So first we put them all on site 1, then all on site 2, all permutations. And in fact, not only were we able to achieve good transfers in certain cases, but in 69% of the cases, or 60% of the cases, we achieve an increase in the purely coherent evolution that would have taken place without the bar. So that's all for now. So energy transfer through a quantum system can in fact be improved as a result of decoherent interaction with the environment. So the previously thought kind of motto that decoherence is bad is not necessarily true. Or there's a whole field of discipline of quantum computing. Okay, so this is gaining momentum. Again, in some cases we could achieve certain transfer even in spite of, or in fact because of interaction with the bar. Yes, the effect persists at physiological temperatures, which is important for biological systems. Yeah, and at the moment we're working on something new, also in photosynthesis, but yes, this work doesn't slide just to continue. So thanks to my supervisors, Maja and Francesco Utuje, our collaborators in Singapore, and more recent work which we're doing with Remco and Mandela. Yeah.
Now we have like 2 minutes to get lunch, so all questions at lunchtime.
My poster was proposing a method for measuring interlayer interaction in Smectic liquid crystals. The problem is actually theoretical, and it is a serious problem, but on the other hand it's very straightforward, so I hope it will be possible to follow also for those who are not experts in liquid crystals. Smectic liquid crystals are very similar to pneumatics, only that they do not have only orientational order but also translational order, so their structure is layered. The molecules are arranged in layers. Now there are a whole zoo of Smectic phases. For example, Smectic A, where molecules are oriented perpendicular to layers, and Smectic C phases, which have tilt. Now there are also a lot of different Smectic C phases, because tilts in every layer can be different. And these different Smectic C phases also change one into another with temperature. There are a lot of interactions between the layers and inside the layers, and all of these interactions affect these phases. inside each layer on the layer. This free energy model is quite complicated, and we also do not know all these constants. But it would be nice if we knew a little bit about their values. Now, if we instead of multiple layers take only 2-layer films, then this equation that I showed before simplifies so that we only have 4 different parameters left and only 2 degrees of freedom. Because tilts in each layer are the same. We can say that it's quite symmetrical. It is symmetrical, and on the both sides, here and up, we have air. So there are actually no interactions between the air and the molecule. These constants A and A1 are temperature dependent, and T0 here is the temperature of the transition from Smectic A phase to Smectic C phase. This BQ, we call this bi-quadratic coupling. Why it's interesting to study 2-layer films? Because they can be achieved experimentally, and because the equations that we get are simpler, we can actually predict system behavior and how it depends on these constants that measure interactions between molecules. Now, if we take this free energy equation and minimize it, we get 4 stable states. The first one is Smectic A state, where theta is 0. The second one is when the molecules are showing like that. The both projections on the plane show in the same direction. The third is when molecules are like that. So alpha is 90 degrees. I will just show once more that picture over before. So alpha is actually half of this angle in between. This is the molecule in the lower layer, and that is the molecule in the upper layer. And the fourth one is neither this one or this one, but it can be rotated in any direction. Molecules in one plane with respect to another plane. Now, some of these states are stable only with some temperatures. And if we take a look at the phase diagram, we see a phase diagram is plotted with respect to the BQ, because in that way we get very interesting results. Now, we see that there are certain areas of the phase diagram that correspond to different states. Now, in this area here, we have coexistence of the second and third stable states. So this one and this one. And here we have only this one. This is called anticlinic structure. And this structure here is called synclinic structure. This means that it shows molecules show on the same side. But up we have 4 states. So in whichever angle, it can show in whichever angle. Now, if we take a look at the systems which have BQ lower than 0, and if we, for example, if BQ is somewhere here, then we start to increase the temperature. So the system will go from this state, from anticlinic state. Here it will be still anticlinic. Here still anticlinic. Although both phases can be minimum in this area here. But here at this point, it will turn like that. Now, if we would lower the temperature again, it wouldn't turn actually a continuous transition from anticlinic to synclinic state, and if you would lower energy, also the transition would be the same. It would be continuous transition. Now, if I represent this in another way, so here I plotted the free energy versus alpha and theta, so this angle around and the tilt. And we can see if we are increasing the temperatures, then here we have only one stable state. This is alpha is 0, so molecules are showing in opposite direction. Here we have two stable states. So this is in the area where we have hysteresis. There are two local minima, and both are fixed. They're just each one of them is getting deeper or less deep. So here we have only synclinic state. However, if we have a continuous transition, then the free energy graph changes in the way that minimum is not fixed, but it travels from one side to another. So we have only one local minima at a time. Well, my final result was actually this equation, which represents these boundaries. These are actually the boundary temperature, not temperature, but the boundaries for example, for hysteresis, or on the other hand, for the continuous transition. So the both phenomena are given by the same boundaries, and from these equations, we can actually get out these parameters if we measure the temperature dependence of the system. So we can measure, for example, the theta, how the angle theta changes with temperature. Okay. There were also already performed some measurements that showed on the hysteresis. Here is shown temperature dependence of relative optical reflection, intensity for two different polarizations of light. And we can see here that here are different n's. So n actually represents the number of Smectic layers. So the n is 2 is relevant for our case. And we can see that here jumps up, and if we lower the temperature, it will go down again at some different lower temperature. So to conclude, the free energy for many layer system is a complicated function that depends on many parameters and also many degrees of freedom, so it is hard to predict anything from that system. But for a two-layer system, equation simplifies, and by measuring, for example, the dependence of theta on the temperature in two-layer films, we can learn about values of A, A1, B, and BQ. And some experimental results already give a prediction. Any questions?
Question?
Experimentally, to achieve this just two layers, that sounds difficult. Do they do it in like a suspended film, or do you know how?
They actually, well, I'm not an experimentalist, but they like put it in the circle, and then they like fall. They put it up. They are enlarging the circle. So if the layer, the film becomes thinner and thinner, and they actually know.
It's just like freestanding film.
Yeah, it's just like freestanding film. And they actually know that looking at some dependence of how the light changes when the light travels the chandeliers are in different positions. They actually get the step-like function. So they can actually tell, like, here are 4 layers, here are 3 layers, here are 2 layers. And it's quite nice.
Okay, thank you. Helene?
It's about making dynamic polymer subsystem, and most precisely to make self-oscillating surfaces. So I will first introduce what is the class of responsive material, because basically we have a lot of projects running with responsive material. So the idea is that when you have your material, you can apply, for instance, a current change in humidity, in pH, or to apply a UV light, for instance, and you will have the property of your system that will change. So the change can be, for instance, their expansion. This is, yeah, it can be 3D, the expansion is 3 dimension, 2 dimension, and so on. It can be also deformation of the film. So Robin showed last week, you can have this freestanding film that curves. But also you can have deformation, surface deformation. So in this case, the film is stuck to a glass plate, for instance, and then it will induce deformation at the surface. So in my case, for this project, I'm working with UV light and yeah, film stuck on the surface, so you will have surface deformation. Surface deformation already been studied and, in our book, and what has been succeed is that the previous pages she was able to make 2 kinds of responsive surfaces. First of all, she could make it irreversible. So here, when she turns on the light, you have the deformation that occurs, and if ever you switch off the light, the deformation stays. But she was also able to make it reversible. So in that case, when you switch on the light, the deformation occurs, but if you switch off the light, it goes back again. And it's reversible, it can happen many times. So she could do that by playing with the chemical composition. Yeah, I won't go too much into detail, but yeah, basically you put or you remove an inhibitor to your system. And now what I'm aiming at doing is to make it self-oscillating. So to do that, what does that mean is that you keep the UV light on and the deformation goes in and out. So this is quite challenging. So how do we do that? We put a photoresponsive molecule in our matrix. So for the one, not too much of a chemist, photoresponsive molecule basically is that you go from a trans state, so when the molecule is like that, to the cis state, so you have a molecule like that. So you really have deformation of your molecule. And this happens by exposing a different wavelength. So by putting at 365 nanometer, you will have cis state, and then if you want to come back, you can expose at 4 or 5 nanometer, or by increasing temperature, for instance. So just to know that the trans state is the one that is the most favorable. So for the first instance, if you don't apply anything, you will have mainly trans state. And it reaches an equilibrium. It's not like if you put 365, you won't have 100% of this one. It always stays as an equilibrium. So that's the idea, and what we do is that we embed this molecule into a liquid crystalline matrix. And the idea is that we illuminate it, and here you can see that we have, when it will isomerize, you will have a reduction, the dimension will decrease along the parallel axis to the molecule, and it will increase in the perpendicular direction. So that's the trigger we are using, and that to make this deformation happening. Yeah. So now to make it really controlled and so on, we use the chiral nematic phase. So we already discussed of it, and the idea is to make the pitch change. So yeah, the reminder, the pitch is the length between here and here. So in that chiral nematic phase, we did put this photoresponsive molecule, And the idea now is first we put a mask. So this is just a mask, and we illuminate it with a linear UV light. And the areas that are not exposed will stay like here, and when the parts that are exposed will increase. So the reason is, as I mentioned before, because we go from trans to cis, and we decrease the order, and we increase we increase the pitch by decreasing the order of the system. So that was what was done to have this reversible and irreversible deformation. But now we want to go to this self-oscillating deformation. So to do so, we are going to use a circularly polarized UV light. So the idea is that when we start with a pitch which is smaller than 365 nanometer. So 365 nanometer, we call it the wavelength at which we will excite the photoresponsive molecule. So as I explained before, when this one is isomerized, we go to a larger pitch, and the idea is to make the length of the pitch match with the wavelength of the UV light. And so if the wavelength matches, we'll have this bright reflection, and basically the UV light will be reflected, and it won't go within the whole film, and the molecule will relax, and then we come again here. And eventually we hope that we can achieve this self-oscillating deformation using this trick. So just a little bit of chemistry. These are just an overview of the molecule we use. So this is to induce the chirality. This is the molecule we use to have this photoresponsiveness, just an initiator to initiate the polymerization of the system. And this is an example of the molecule the previous PhD used to create the responsible and reversible and irreversible deformation. And the idea now is to go to this molecule. So why we want to work also with this one is that when we do increase the pitch, we induce deformation, but it's also that we will bring some free volume. And this is not wanted by the system. So the idea is by using those hydrogen bonds, we can compensate with this free volume creation, because the hydrogen bond, they can rearrange with another body just above or under, and then it will compensate for this free volume creation. So that's the idea. So the first result are the following. So this shows that we can have these deformations, and if we look at the scale, we start with a film of about 10 micrometer and a roughness about 150 nanometer, and in the end we can achieve that deformation up to 1.5 micrometer, which is really a lot because it's more than 20%, and it's difficult to explain that just based on free volume creation. So the idea now we need to find another way to measure that, because this measurement was done as a replicate. So basically what I did, you put some PTMS, which is not cured, you put a polymeric film on top of it, your mask, you illuminate it, and while this one is deforming into the PDMS is cured. So basically you just make an image of what you are doing, and you measure your image. So now what we want to do to confirm this result is to make use of two different phases. So what we want to do is to make a cholesteric phase next to isotropic phase, and so on. And the idea is that when we will expose UV light, the isotropic phase will not increase or deform as much than the cholesteric phase. And yeah, so the idea is that then we expose to UV light, and this one will rise, and this one will more or less stay the same. So that was the idea. And now, why do we do that? there are many, with a bit of imagination, we can find many different reasons. So you can use it in microfluidic, for instance, but also you can use it for micro-robotics. You can use it for, why not, solar cells, like vibrating for the UV light beam, so that it propagates in a certain way, and so on and so on. So that's it. And yeah, so looking forward.
So in this case, when you have like cholesteric phases and cholesteric phase and isotropic phase, how do you intend to achieve that? I mean, will you have like different temperatures or different liquid crystals?
To have this cholesteric isotropic cholesterol,
Yeah.
what we do is that you first here. First, you prepare your film at the right temperature to have this chiral phase. You polymerize it through a mask. So you put a mask, and then only the exposed area will polymerize. It lasts not even 5 seconds. Then you remove your mask. You got higher temperature, so basically isotopic temperature, and you fully polymerize the system.
Okay, thank you.
I'm going to present a project which deviates from the topics we're using, like the liquid crystals, because my current project is on the cell motility. So we are trying to understand this phenomenon of cells that migrate collectively. So the phenomenon is common in many biological processes, as you can see, like the process of root healing or morphogenesis or expansion. Cells move collectively, but up to now, people don't fully understand the mechanisms that drive this phenomenon. And many people have tried to establish models for this migration, but still these two questions, like the forces that transmit through the cells, how do they transmit through those cells? Or what is the major mechanical response? These two questions and the others are still debatable. People give different answers, like people say, we have some leading cells which move on the edges and the cells at the bulk will follow. Others will say no, cells move as a unit, and that's what the trend that I'm going to show, because in my results I'm going to see that even cells inside the bulk, not on the leading edges, they move faster, not only the leading cells. And that will give us some new insight. So, our project is based on different research, experimental observations. For example, experimentally, people have found that at the midline of a layer, the stresses oscillate with time. And these oscillations, they are in phase with the fluctuations of the cell area. This is the area covered by the cell as they move. And they are out of phase with the strain rate, which measures the rate at which cells are deformed in the layer. So this phenomenon shows that the medium is elastic. And that will be our first ingredient in the model. So that means the layer is going to be considered as a continuum medium, the elastic medium. And also they found that the distribution of stresses are maximum at the center and minimum at the edges. I'm going to go back to that later. So our minimum continuum model will be one-dimensional, to make it simple, but I will upgrade it to two-dimensional later. So in this case, before we're gonna our layer in its initial state has this dimension L0, and as it spreads, I can calculate or I can measure the displacement of the layer with respect to its initial position. And that will be my first dynamical variable, which is U. It's a field, U of X and T. But I also need to know something else, and that's the main thing I'm going to talk about. That's the active processes in the cell as they spread. As the layer spreads, some active chemical processes occur. They are coupled to the cell, to the layer elasticity. And my main interest are the active effects from the myosin motors. These motors, they consume ATP and hydrolyzes into ADP and inorganic phosphate. And the chemical potential difference from that reaction will give me the effect, the active effect, which are contractile in my case. So the way I'm going to do it is I'm going to consider that I can find the concentration of ATP at equilibrium. So this is how I can write the equation for hydrolysis at equilibrium, ATP hydrolysis, and this will be the concentration of ATP, and I'm going to claim that when the motors are still active, I can find a concentration of field such that as the active processes are exhausted, my concentration will become C0 at equilibrium. So that is my main thing. So that means I have two dynamical process variables, U and C, and I need to find two differential equations that I'm going to solve and see if I find the same thing as experimental results. Okay, so the first thing, because the layer spreads on the substrate, the layer interacts with the substrate through the focal adhesions, and that's why I have this frictional interaction of the layer to the substrate, and also the cells interact with its neighbors through the cell-cell junctions. I'll have, those are the stresses, and this will be like the tractions, and this will be the spreading force. In my minimum model, I'm going to say that the spreading force, which we think arises from the cell polarization, are going to be uniform throughout the layer, but because the center of mass of my layer doesn't move, so the center, cells of the center don't move, but other cells move uniformly in this direction and in this direction. That will be my spreading process. So this will be the passive stress, which are due to the elasticity of the medium, and this will be the active stress, which are due to the effect of the myosin motors, and they are logarithmic. And this concentration of excess ATP has this equation, dynamical equation. When I consider that my system is not conserved, so I have a quantity which is the concentration of ATP, which can be exchanged with the external medium, which in this case will be like the extra matrix, where the cell moving, and this is the diffusion, and that will be the active part too. So my goal is actually to solve these two equations. That is right. So first of all, I'm going to what happens if there is what we call fast excess ATP relaxation. That means at a long time, I can neglect the effect, the active effect, and see what happens. In this case, I have only one single equation, which is not difficult. I can solve this analytically. And this will be my effective compressional modulus, which can either be positive or negative. When it is negative, it means that my layer has some contractile instabilities, and this paper explored that case with Christina and Shraditya. But me, I'm interested in the case where the layer is stable against the global contraction. So I'm going to consider this quantity to be positive. And when I solve this, I can find the stress of the layer, inside the layer, and they agree qualitatively with the experimental one, but these are dimensionless quantities. But still you consider the stress is maximum at the center and minimum at the edges. And my system also spreads, expands, which is something also I want to see, because this is the plot for displacement. So these values at the boundaries shows me how much the layer is expanding from this question. That means, for example, at t equal to 3, if I take this, I take this value plus this value minus, that's like twice this value, plus this, will give me how much my layer has expanded. So that means using this simple equation, I can find more like the qualitative observations which are experimental, and my layer expands, but I'm missing something, because in the experiment they found that these stresses that propagate inside the layer, they are due to something that which is a wave-like, which are like mechanical waves. But I cannot see this because my medium is overdamped. There is no way I can see propagation of waves. But because we see them, that means there is something else which is involved. And that is what I'm saying, the active parts of my system, which are the myosin, the activity due to myosin motors. So when I couple the second equation to my first equation and solve it, I start seeing something like this wave-like. These are the plots for the stress. The first thing I saw is that the order of magnitude of my stress is the same, and for the same time scale. And qualitatively, I can find that the stress are maximum at the center, and they are wave-like, like in experimental results. But the problem, you see that they are not quite the same, because when I solved this, I made my system linear, so I analyzed the logarithmic part of my active stress. I used the first order for the logarithmic expansion. So in my next step, when I use my equation the way it is with non-linearities, I'm sure I'm going to find the same thing. And when I solved these systems, I used free stress-free boundary conditions, and there is no flux. And initial conditions, there's no stress at the beginning, and at the beginning my system was at equilibrium. But when we see that for the velocity, because as I told you, the cells are free to move at boundaries, that's where they move faster. And I think my velocity plots are quite the same like the experimental one. You can see we have inward velocities at the boundaries and nothing at the center. As I told you, the cells at the center don't move, and you have wave-like things. And also the order of magnitude is the same. And also we have something that we predicted, that the contractile activities due to myosin motors are higher at the edges than the center, which is true because that's where we have more traction forces. But this picture, which maybe this should be maybe the first picture I should show, because the wave-like phenomena that they saw, they call them X waves because they look like X. This is the plot for the straight wave, as I told you. That shows the deformability of the cells and the spread. I don't know if you can see it there, but for people who are maybe nearby, my straight wave also shows the X patterns. If you maybe use my laptop, you'll see it. And people can think that maybe my layer is going to expand indefinitely, but no, that's not true, because at some time it has relaxes. So that's why I try to plot to see how the length of the layer with respect to time, and I found that at given time around 1000 minutes, my layer is going to stop spreading. And I checked with the analytical steady state solution for the length, and they agree. So in order to solve my numerical solution, I have to use stability analysis, and I think Christina and Greg, they talked about it, how to use like stability analysis to solve some equation. That's what I used here. And I was interested in this region, the region of propagating waves where the modes are oscillating but also stable. So I used parameters from this region to solve my system. So I hope that I showed you that a minimum model, which is one-dimensional model, can qualitatively agree with experiments. So in this case, our model coupled the elastic properties to the active behavior of the Marais motors, and you can see many experimental observations that agree with my theoretical results. But we know that actually in the real life, this kind of system, they are non-linear, even if I use the linear equations. So I have to include some non-linearities, because if I don't include them, even those propagation of waves, they are going to decay with time. But I want something which is sustainable, which sustains. So I'm going to include the non-linearities, and I'm going to also upgrade my system to 2D, because that's what the substrate is 2D, it's not 1D. Thank you very much. Usually when nobody asks a question, my theory is that you didn't understand what I said, not because it is difficult, but because maybe I didn't explain it well. So I need somebody to save me and ask me a question so that people will think that they understand what I said.
That's a challenge, isn't it? So if you go to one of your latest figures, in this blue curve, you have very definite steps. Is it due to your computation, or is something happening?
You mean this one?
Yeah.
I think that.
Some sort of oscillations, but is it because of calculations? Or is
So this are due to my. So this one is this one. I still have problems with it because it is due to this part, which I don't know why. I think it's my code, which is maybe somewhere they have some bugs.
Okay.
But these ones I think that's how they should look at, because the oscillations. And when I looked at an experiment, they also plotted.
See oscillations.
Yeah.
Okay. So can you figure out how big those oscillations are?
How what?
Can you measure the oscillations from the curve?
I think I can, because before I came into the ICAM, Christina asked me to find first the wavelength of my wave and the frequency. So that's something I have to figure out, and I think they help me.
Okay,
Yes.
just one more question. Sorry.
Nice.
So in a sort of a standard picture of adhesive spreading of a passive system, you usually think about the spreading force acting at the boundary.
Yes.
Rather than throughout the medium. If you because of the contact forces of so if you treat the forces as really being localized at the boundary, do you expect to see a very different result? How important is it that the spreading force is acting very far into the bulk?
Okay, so I think I didn't say it, but it is written there.
You said it was because of the polarization of the zone.
Yeah, and I used like a sine function, which is not true, because it's like I have forces which is the same throughout here, and throughout here, nothing here.
Right.
But I think the usual is to use maybe a tangent function.
I mean, the usual thing for a viscoelastic solid on another adhesive solid is to have the force acting only at the edges. So it'd be more like a delta function.
But isn't that idea the same thing like for who are saying that there is a liters, like living cells, like at the edges of?
Maybe that would correspond to that case, but you know.
Yeah, that's why. So in this paper with Serapi Kamal and
Yeah.
Ali, they contradict that idea. They say no, there is no such thing as living cells. All cells they move because, as I said, I think that my forces are due to polarization of cells, and all cells are polarized, not only the living cells. So that's what I think.